guys, nice to see you. See, only the most resistant could make it. Not easy to come to the last section, right? So, who will recall what we discussed last time, Wednesday? We continue to deal with moment of inertia calculation and considered the rolling rigid body. So we kind of split this motion of rolling rigid body into two components, translational and rotational with respect to the center of mass. Then we have shown that it's possible to consider this combination of two motions as just rotation, but not about center of mass, but about a point where this rolling rigid body is touching the surface over which this rolling is happening. And based on that, we determined moment of inertia of rolling object with respect to this particular point, so-called instantaneous axis of rotation, because it always changes as body is rolling. And in order to do that, we applied considered previously parallel axis theorem, which allows us to determine moment of inertia quite easily if we know already moment of inertia in the center of mass. We have shown that kinetic energy of such rolling object consists of two components. One is translational, another is rotational. And when we want to determine, for instance, when a rigid object is rolling over some inclined plane, the velocity of the center of mass. So when we have conservation of energy, we transform potential into kinetic. We need to take into account the fact that initial potential energy is transformed into two components of kinetic. There is rotational kinetic energy and translational, like motion kinetic energy. So this factor should be taken into account, and that is the way how you need to approach. So today we continue with rotating rigid objects, and in order to describe parameters which are related to dynamics already, we need to introduce so-called torque. So that's let's say some parameter which defines how much external exerted force tends to rotate a rigid body about some given axis of rotation. So far we were looking for correlations between kinetic parameters like position, velocity, and acceleration for translational motion. So we have some equivalence in rotational, that is angle, angular velocity, and angular acceleration. But today we proceed further and we're looking for some equivalent of force, which we considered previously for rotational motion, and that is torque. So let us first introduce this new parameter torque. So for that, let us consider a head of a bolt and some wrench which tries to rotate this bolt. So we have the wrench. Well, some not the most advanced wrench, but whatever. Imagine that it's a high quality wrench. So we have some center of this bolt, and that is, we define it as point O. So that is the axis of rotation, which goes perpendicularly to the plane of our screen. And here, at some point, we have force F exerted to this range. So this will be the position vector of the point where external force is exerted to the range with respect to the axis of rotation. And if we look here for some axis x and axis y, so this force will be exerted at some angle phi with respect to horizon. So we can consider projections of this force vector on axis y and z. So this will be f times sinus phi, and this will be f times cosinus phi. So we see that this projection on axis x does not make any efforts to rotate the bolt, since it goes through the line which connects the center of the bolt and the point where force is exerted. So there is no lever for rotating. Obviously, there is only this component along axis y, which tends to rotate the bolt. So torque is defined as the product of this distance between the axis of rotation and point where force F is exerted, and projection of force on axis y, F times sinus phi. So what we can do here also, to make it more general, we can kind of extrapolate this line which defines force vector and then draw a perpendicular from the axis of rotation towards this line. So this will be some distance d, and taking into account that this angle is also phi, we can write that d is equal to r times sinus phi. So taking this into account, the torque is defined as force F times d. So this d is so-called moment arm or lever arm, and this is the parameter which some additional parameter which we need in order to define how much exerted force F will tend to rotate some given rigid object with respect to some axis of rotation. In this case, we have ball and axis of rotation which goes through the center of system. Obviously, that several parameters matter. First of all, distance of this point where force is exerted, and also orientation of the force. Since distance can be different and it doesn't mean really much because of different orientation, then we introduce this parameter d, which will be a unique parameter for given condition, and that is called like moment arm or moment lever. So far we defined only magnitude of the torque, and obviously it's a vector, so we need to define also orientation. However, before that, we need to define the sign also of this torque and introduce net torque. So let us consider some rigid body. Here will be axis of rotation, let's say O, which goes through this point O. Then we will have two forces. So here will be d1 for force F1, and here will be d2 for force F2. So now, what do we see from this image? That force F1 tends to rotate this rigid body about axis O counterclockwise. As opposite to F1, F2 tends to rotate it clockwise. So they kind of counterbalance each other. We have effort to rotate counterclockwise, and here clockwise. So the torque originated from force F1 will be given as F1 times D1, and by definition, so it's agreed that torque which tends to rotate a rigid body counterclockwise is considered to be positive. So it's larger than 0. If torque tends to rotate so counterclockwise is positive, clockwise is negative. So if we have this F2 times D1, this will be negative because it tends to rotate in the opposite direction. And obviously, when we deal with the net torque, that will be torque 1 plus torque 2. It will be F1 times D1 minus F2 times D2. Okay, so let us define also orientation of torque vector. We have some three-dimensional system of coordinates, x, y, z. And let's say we have some point P. Here is exerted force F. And here is position vector, which defines this force. So there is some angle between them. So direction of the torque for a vector is defined as the cross product of position vector and external force. So that means that the torque vector will be perpendicular to the plane where these two vectors are defined, and in this particular case it will be oriented along axis z. So we have torque vector here. So after we have defined the torque, magnitude, and orientation, we can consider a rigid body under some net torque. So let us consider some system of coordinates. X, y, and some arbitrary shape rigid body with respect to some axis of rotation which goes through the center of this system of coordinates. So since we have a continuous body, we want to divide it into some small elements. That's how we approach every time when we have some continuous rigid body. So let us define here some small element with mass dm at the distance from the center, like the origin of this system of coordinates, and automatically also distance to the axis of rotation, like position vector r. We assume that there is some tangential force, tangential means perpendicular to the position vector, dft exerted on this small element. So if there is some mass and some force exerted to this mass, according to second law of motion, we will have some tangential acceleration. So we can write that dft is equal to at times dm. And what will be the torque exerted to this small element? Since dft is perpendicular to position vector, it will be defined as the product of distance, this radius, times dft. And instead of dft, now we can substitute its expression according to second law of motion. So we'll have r times at times dm. Now, what we can do with tangential acceleration? We remember that at can be expressed as dv over dt. How do we express linear velocity in terms of radius and angular velocity? So that is v is equal to r times omega. Now, if we take derivative of linear velocity vector over time, we get r, which is constant in this case, over times d omega over dt. So that's first derivative of angular velocity, and that is equal to r times alpha. Alpha stands for the angular acceleration. Now we can substitute it here, and we get expression for the torque exerted on this mass dm with respect to axis of rotation going through the center of coordinate O will be given as r squared times alpha times dm. So that is true about the small element with mass dm. Obviously, we want to know what will be the total torque exerted on the rigid body. So for that purpose, we want to integrate it. So we can write net torque exerted on this rigid body will be equal to integral of r squared times alpha dm. So what is about this angular acceleration? Any comments about this? It's constant because no matter what, where we pick up a point, it will be the same for all points of this rigid body. That's definition of the rigid body. So that's why we can take out this acceleration, angular acceleration out from integral. Here we'll have r squared dm. And any comments about this? What is this? Moment of inertia, what we calculated previously for continuous bodies. So here we can write that net torque exerted on a rigid body will be equal to angular acceleration times moment of inertia. Of course, with respect to the given axis of rotation. So we can write here that it's equal to alpha times I. So if you compare now second law of motion, F is equal to acceleration times mass. So we see that we have direct correlation between these parameters. So it's kind of equivalent of second law of motion, which is presented in the form applicable to rotational motion of rigid bodies. So once we define a rigid body under a net torque, we can proceed further and introduce another parameter, which is called angular momentum. So, as you remember, not so long time ago, we introduced linear momentum as a product of mass and velocity vectors. And we have shown that for a closed system, linear momentum vector remains constant. So, what is closed system? External forces are compensated, and or they don't exist. In this case, in the closed system, total linear momentum remains constant. That's conservation of linear momentum. Something similar we will also show with angular momentum, which is applicable to rotational motion. So that's also very important, which can be kind of very handy and helpful when we solve some problems for rotational motion of rigid bodies. So now, for introducing this angular momentum, let us consider a three-dimensional system of coordinates x, y, and z. Here will be some point A with linear momentum vector P and position vector R. Who will remind me how we define second law of motion in terms of linear momentum vector? Net force is equal. So we remember that net force is equal to m times a. And what is a? A, acceleration, is first derivative of velocity vector over time. So we can write that net force is equal to m times dv vector over dt, and that is nothing else as dp vector over dt. So first derivative of linear momentum vector over time gives us the net force exerted on the body. So here we can write dp vector over dt. And the net torque exerted on this body will be, by definition, which we already know, is position vector cross product with the net force vector. And instead of that, we can write first derivative of linear momentum vector. Oops. Okay, so that is the definition of net torque exerted on this point A with respect to some axis z. So now what we can do here, I claim that if we add here dr over dt cross product p, so let us put it in parentheses so we see what we added. Nothing will change. We still can keep this equality. So can you explain why this claim is valid? d r over dt would be the velocity vector. This is linear momentum. Yes. So that means that these two vectors will be parallel. If they are parallel, so we know that cross product is magnitude times sinus angle between two vectors. Angle is 0, sinus is 0. So this cross product will be equal to 0 by definition. So this is equal to 0. If we add 0 to something, nothing will change. But now we can write that this is equal to d first derivative over time of the cross product of position vector and linear momentum vector. So that comes from the rule of taking derivatives of the product of two functions. So if you have function fx, f is a function of x times g is a function of x, and we take derivative, so we get similar expression to this. So that's why we can go from this to this. Now, when we have it, we have some parameter, some new vector, which is cross product of position vector and linear momentum vector. So we can introduce a new parameter dl vector over dt, where L is cross product of position vector and linear momentum vector, and that stands for angular momentum vector. Which obviously, according to the rule for cross product, will be perpendicular to the plane defined by these two vectors, position vector and linear momentum vector. So it will go along axis z. So units for angular momentum will be kilograms times meter square over second. So what is also necessary to highlight that we see here, because we expressed initially net torque as change of the angular momentum vector over time. So we can write that net torque is equal to dl over dt. And we can write here that change of the angular momentum vector will be expressed as net torque times delta t if we consider that this net torque constant. So that an analogy with the definition of change of linear momentum vector, we have shown that it's equal to the impulse of force, which is product of force exerted on the body times time interval during which this force was acting on the body. So in this case, the change of angular momentum vector is equal to angular impulse of net torque. So this very similar approach, we just operate with different parameters. And if net torque is not constant, obviously change of angular momentum vector should be defined as integral of this time-dependent torque over time. So now let us consider angular momentum vector of a rigid body. So far we had just some point body A. Now let us consider what we will have with rigid body. Before we start with that, I need to highlight that we will consider the most simple case when we have a symmetric body and the axis of rotation will go through the center of mass. In that case, orientation of the angular momentum vector will coincide with the orientation of angular velocity vector. That is not going to be true for arbitrary shape body and some random position of the axis of rotation. So that will be that discussion definitely goes beyond our the scope of our course. So we definitely consider the simple example. So for this purpose, let us have some symmetric rigid body, which is some disk. Here is this axis. So we have axis X, axis Y, axis Z. So axis of rotation, that's axis Z, and this disk rotates clockwise about axis Z. So angular velocity vector goes along axis Z, and that also will be true for angular momentum vector with respect to axis Z. So now let us consider some point with mi at distance from this axis ri and velocity vector vi. So this will move along some circular trajectory. Now what will be the angular momentum vector of this specific I point? So since velocity vector is for circular motion is perpendicular to the radius, we can write that angular momentum vector will be mi times vi times ri. So now, so this is just a linear momentum, and this is the distance of this point with respect to the axis of rotation. Now we remember that linear velocity can be expressed as product of ri times omega. So that will be mi times ri, and instead of vi we get ri times omega. So we end up with mi times ri squared times omega. So omega comes without index I because it is rigid body, and that means that omega is the same for any point. So that is true for this given point on the rigid body, and we want obviously to get the angular momentum vector for like all rigid body. So what we do in this case, of course, we specify with respect to which axis we calculate this. That will be sum for all these small elements. In other words, we can also integrate, but here let's consider this sum for all angular momentum vectors of each element I. So that will be sum for I times mi ri squared times omega. So this we can write like this. Will be mi ri squared times omega. So omega can go out from this sum since it's a constant. And this guy is nothing else as moment of inertia with respect to axis z. So eventually we get that angular momentum vector is equal with respect to axis z will be equal, its magnitude is equal to I z times omega. So let us take the derivative of this angular expression for angular momentum, dLz over dt, like rate of its change over time, that will be Iz times d omega over dt. Iz is a constant, it doesn't depend on time. If we don't change the position of axis of rotation and rigid body doesn't change by definition its shape, then it remains constant. So that will be Iz times alpha, which is angular acceleration. And we remember from previous discussion when we considered the rigid body under net torque that moment of inertia times angular acceleration gives us the net torque exerted on this rigid body. So here we get some relationship between key parameters which describe the rotational motion of rigid bodies. So we operate here with angular velocity, angular acceleration, moment of inertia. So these guys stand for equivalence of velocity and acceleration and mass in translational motion. But also we have features which define dynamics. So we have net torque, which is equivalent of net force for linear momentum vector definition. And actually we have the angular momentum vector, which is directly equivalent of linear momentum vector. But this is for translational motion. So you see these relationships between all these key parameters. And what is important here, that change of angular momentum vector over time is defined by net torque exerted on the rigid body. So if we have a closed system and external, so definition of closed systems, that external forces are either absent or they are equal to zero because they compensate, the net external force is compensated. If force is equal to zero, net force, and then net torque is also equal to zero by definition. So for closed system, we can write that net torque vector will be equal to zero. And that means that from this relationship, which we had for different parameters of rotational motion of rigid bodies, that first derivative of angular momentum vector over time is equal to zero. Means that angular momentum vector remains constant for a closed system. So that is the statement of conservation of angular momentum vector in closed system, which is quite helpful because we remember that angular momentum vector for a rigid body is defined as, well, let's write here in just absolute values, a moment of inertia times angular velocity. So if we consider that this system of a rotating rigid body is closed, then we can write that initial moment of inertia times initial angular velocity will be equal to final moment of inertia and final angular velocity. So if you a classical example of this ice skiing, when they reduce moment of inertia, they start to rotate but then reduce moment of inertia by moving hands from far closer to the axis of rotation, then this spinning becomes quite accelerated. So what happens? We have this principle of conservation of angular momentum, since you know that moment of inertia is proportional to r squared times m. So r, distance, actually is a key parameter which defines the moment of inertia. So change of the radius of this distance from the axis of rotation will have a strong impact on the value of moment of inertia. Since moment of inertia decreases quite significantly, in order to keep the angular momentum vector constant, our angular velocity should increase. So the frequency of rotation increases. And that, of course, is applicable for different cases, not only for this. That's probably most common as an example. So that, of course, can be quite useful for application in different cases when rotating rigid object can be considered as a closed system, means the net external torque exerted on this system is equal to 0. So, summarizing our today's discussion, we introduced the concept of torque, which is equivalent of force for rotational motion. It defines the tendency of exerted force to rotate a body. It's equal to the force magnitude times the moment arm or moment lever. So means it defines is determined by the orientation of force and also position of this point where force is exerted with respect to the axis of rotation. The net torque exerted on a rigid body is equal to the product of angular momentum, moment of inertia and angular acceleration. Then we also introduce another important parameter, which is angular momentum. It's equivalent of linear momentum in translational motion. So we have definition of angular momentum vector as a cross product of radius vector, position vector, and linear momentum vector. So it's always perpendicular to this plane when we're talking about a point with some mass m and like linear momentum vector p. We have shown that there is a relationship between the net exerted torque on a rigid body and rate of changing of angular momentum vector over time. So net torque is equal to first derivative of angular momentum So net torque is equal to first derivative of angular momentum vector over time. And what is really important that for a closed system, we have net torque equal to 0. And that means that there is no change in angular momentum vector. If there is no change in angular momentum vector, it remains constant, means that we can apply a principle of conservation of angular momentum vector, similar as we did for linear momentum vector. So which definitely can be quite helpful. With this, thank you very much for attention. Have a good weekend and see you next week.